4 at most. Then remember that over real numbers, all the polynomials of odd degree, all they have at least one root. Therefore, there are no cubic polynomials with 0 roots. Now, let us give an example of a cubic polynomial with just one root. Okay, for example, x to the cube. This is a polynomial which has only 0 as a root. In this case, you see 0 is what we usually say the root of multiplicity 3. But for example, you can also consider the following polynomial, x times x squared plus 1. And you see, x squared plus 1 is always greater or equal than 1 for which real number I substitute to x. Therefore, this factor has no roots, no real roots. Hence, this cubic polynomial has only one root, x equals 0, now with multiplicity equal 1. And now, let us consider the case of two roots. Okay, for example, you can consider x times x minus 1 square. This polynomial has exactly two different roots, x equals 0 and x equal 1. X equal 1 is a root of multiplicity 2, x equals 0 is a root of multiplicity 1. And finally, a cubic with three different roots could be x times x minus 1 times x minus 2. And now let us consider the quartic polynomials. Now, for a quartic polynomial, it's possible to have no roots at all. Consider, for example, x to the fourth plus 1. This is always greater or equal than 1 for each real number we decide to substitute to x. Therefore, this polynomial has no roots. With one root, we can consider x to the fourth. Again, 0 is the only root of this polynomial, and 0 is the root of multiplicity 4. Now, with two different roots, then we can consider x squared times x minus 1 square. Then in this situation, we have only two different roots, x equals 0 and x equal 1, both with multiplicity 2. Or otherwise, we can also consider x times x minus 1 times x squared plus 1. Again, this factor has no roots, and therefore this quartic polynomial has exactly two roots, each one multiplicity 1. Now, a quartic with three roots, then we can consider x squared times x minus 1 times x minus 2. Okay, this is a polynomial with exactly three roots, 0 multiplicity 2, 1 multiplicity 1, and 2 multiplicity 1. And finally, let us see a quartic polynomial with four different roots, x times x minus 1 times x minus 2 times x minus 3. This is an example of a polynomial with four different roots. The roots are 0, 1, 2, and 3, all of multiplicity 1. Take a close look at quadratic polynomials, that is, polynomials of degree 2. They arise in many problems and applications, so becoming very familiar with them would be an excellent idea. A generic quadratic polynomial, p of x, then, is a function of the form ax squared plus bx plus c. The coefficient a has to be different from 0. We're going to be interested in finding the roots of a quadratic polynomial. And one way to do this is by factoring. Let's take a equals 1 and consider that we wish to write x squared plus bx plus c in the form of two linear factors. This would be called factoring the quadratic. So we should be able to write it in the form x plus p times x plus q. What are p and q going to be? Well, here are some clues. When you work out the parentheses, you see that the constant term is pq, which therefore will have to be equal to c. And p plus q, the coefficient of x, will have to coincide with b. Now, how do you find these p and q's? Well, you find them by trial and error, guided by experience. Sometimes you say inspection. These are also all fancy ways to say really that we're going to guess them. Guessing is not a technique to be scoffed at in mathematics or anywhere else, especially if you learn how to do it in an educated way. Here's an example. Suppose you wish to factor this quadratic polynomial. Well, we're going to look for the p and the q among the divisors of 6, and we want two of them that are going to add up to minus 5. So we find rather quickly the factorization x minus 2 times x minus 3. Another example, we look for divisors of the 7, and we find x plus 7 times x minus 1. You see that when you factor the quadratic, its roots become apparent. In this last example, the two roots are x equals 1 and x equals minus 7. Now, suppose a is different from 1, and the coefficients of the polynomial are integers, we can often still factor by inspection, as we say. Here's an example. You play around with this, you fiddle around with the possibilities, and pretty quickly you find the factorization that you want for this quadratic. Okay, but let's notice an important fact. Factoring won't always work. It can't always work. Why? Because anytime you can factor a quadratic into two linear factors, it will have roots. But there are some polynomials of degree 2 that don't have roots, like x squared plus 1, for example. It's never equal to 0. Therefore, no matter how hard you try, you'll never factor it into two linear factors. So this raises a bunch of questions. When is it possible to factor a quadratic? How can we tell? And if it has roots, can we always calculate them by factoring, or is there some other way? It turns out that these general questions can be given a highly satisfactory answer through a technique called
completing the square. That means using a little algebra to get a really strong conclusion. Now, we're going to rewrite our general quadratic polynomial in such a way that just looking at it, we'll be able to tell whether it has roots and what the values of those roots are. Here's a simple illustration of the general procedure. Suppose we try to factor x squared plus 2x plus 2. We can spend all the time we want trying to factor it. We won't manage. Here's a way of seeing why. We look at the x squared plus 2x, and we have the idea of associating the number plus 1 to it. So we break the 2 into 1 plus 1. That allows us to recognize the first three terms on the right as being x plus 1 squared by a notable identity that we know very well. And once we've written our polynomial in this form, it's clear that this quadratic has no roots, because the square of something plus 1 can never be 0. So there are no roots, the polynomial cannot be factored. So this procedure is called completing the square, and now we're going to do it in a general way in the presence of the symbols a, b, and c. In other words, we're going to have some fun with algebra. We take our quadratic, and doing a little arithmetic, we write it in a different way, and again in a different way. Here the point in of this calculation is to have in the parentheses something that we will recognize as the square of something. And then we have another term outside which we bring into these curly brackets or braces, and that's the result we want. We'll see why in a moment. Notation, classical, since forever. The constants at the end grouped together are called minus delta, and delta, capital delta, is called the discriminant. So definition, delta is b squared minus 4ac, the discriminant of our quadratic polynomial. Let's summarize what we've done. We've simply rewritten algebraically our quadratic polynomial in another form. We haven't really changed anything, except that now it's going to be apparent that we can prove the following proposition just by looking at this form. For example, the first assertion. If delta is strictly negative, then the quadratic polynomial has no roots. It's irreducible. Well, that's obvious, because if you look at the quantity in the braces, the minus delta is strictly positive, and you're adding a square to it, so you can never get 0. No roots. Second case, second assertion. If delta is positive, then there are roots, and they're given by the formula that you see. That's easy to prove too, because the quadratic will equal 0, and the quantity in braces is equal 0. That means that 2ax plus b squared equals delta. We solve that equation, we get the values of x that we see. Incidentally, this formula for the roots of a quadratic polynomial is called, logically enough, the quadratic formula. Many students nominate this formula as the formula they're most likely to remember till the end of their lives. A remark, when delta is 0, we actually get just one root, because the plus or minus doesn't matter. And otherwise, when delta is strictly positive, we get two distinct roots. Let's illustrate these results with this example. We want to find the roots of x squared plus x minus 3. Well, here's the general notation for our quadratic and for the discriminant. You should find a place for this general notation in the software of your mind. After all, you'll be needing it for the rest of your life. We see that in this example, a is 1, b is 1, c is minus 3. We calculate the discriminant. It's 13, strictly positive. So there are two distinct roots. We calculate them with the quadratic formula, and there they are. Explore some aspects of the geometry of quadratic polynomials. We'll see that once you understand this geometry, some common questions are rather easy to answer. So, we have a general quadratic polynomial, ax squared plus bx plus c. We'll suppose that its leading coefficient, the a parameter, is strictly positive. What do you think its graph looks like? Well, recall that we had found a way to rewrite our quadratic using this notation with the quantity in braces that you see, and where the delta means the discriminant. Now, once you've rewritten it this way, it jumps out at you that it's going to be the same graph as the graph of x squared, except the graph is going to be squished or stretched. It's going to be shifted up or down or left or right, because you see the x has become 2ax plus b. That is, there's been a dilation and a translation of the argument, and then the values have also been translated and dilated. So the graph is going to look like our parabola graph for x squared, and it's going to open up because the a is strictly positive. If the a were negative, it would be a downward opening parabola. And now we see some cases arise. If the discriminant is strictly positive, there are two roots of our quadratic. That means the graph must intersect the horizontal axis in two places, like so. If delta is strictly negative, there are no roots. So therefore, the graph of the function must lie above the x-axis everywhere. And finally, in the case when delta is 0, there's exactly one root, so this must be a case where we have just exact contact between the parabola and the x-axis at one point. Let's see how this appreciation of the geometry can lead to a very easy answer to a question such as this, which might seem hard otherwise. For what values of x is it true that x squared minus 4x plus 2 is negative? Well, we recognize that we have a quadratic polynomial on the left. We calculate its discriminant. Delta turns out to be 8, and therefore it's strictly positive, so there are two roots. We can find them by the quadratic formula, and here they are. Now, when there are two distinct roots, and a is positive, what is the graph of the function going to look like? Answer is going to intersect the x-axis in 2 points. What are those 2 points, those values of x, where we have these intersects? Answer, of course, they're the two roots of the quadratic, which we've calculated. And now we can answer the question just visually. For what values of x is it true that this function is negative? That is, the graph is below the x-axis. Well, it's obviously the interval, the closed interval, determined by the two roots, and that's the answer. Here's another example of a type of question we can easily answer if we bear in mind the geometry of quadratic polynomials. I'll give you one, ax squared plus bx plus c. The a is strictly positive, and I ask, what is the value of x for which this function attains its minimum, its lowest value? Well, we have this expression that we so carefully worked out before, an alternate expression for a quadratic polynomial. We know the graph is going to look like this, and we're looking for the value of x that corresponds to the lowest point in its graph. Where will that be achieved? Well, if you look at the quantity in braces, misses, you can see that it's something positive, and then there's a constant. So it'll be least when the something positive is 0, that is when 2ax plus b is equal 0. That's when x is equal minus b over 2a. So this special value of x, which I've labeled xm, means the value of x for which it will be at the lowest point of the parabola. Let's take an example. You want to minimize the function x squared minus 4x plus 1. You want to find the minimum value of that function, and you want to identify the point where this minimum is attained. We calculate xm. It turns out in this instance to be 2. Now the function has value minus 3 when x is 2, as you can check, and so the minimum value of the function is minus 3. Now here's an example of a somewhat more subtle nature. We again want to calculate the minimum of a quadratic polynomial. However, we now restrict the study to the interval 1, 2. How do we proceed? Well, we calculate the minimizing point for a quadratic function. Turns out minus b over 2a in this case to be 1/2. And we notice that 1/2 is not in the interval over which we wish to take the minimum. That is, 1/2 is not in the interval 1, 2. If it were in the interval, then of course that would be the minimizing point. But it isn't. In fact, it's to the left of the interval, as you can see. The fact that it's to the left of the interval allows us, geometrically, to see that the function f is increasing on the interval 1, 2. It gets bigger as you move to the right. Therefore, if you're interested in minimizing f, you want to be at the leftmost point of the interval 1, 2. That is, at x equals 1. That must give you the minimum relative to that interval. So we calculate f at the point 1, and the minimum is 2. We're going to continue fun with algebra in the next segment when we do polynomial division.
Of the quadratic polynomials in practice step. We want to write both these two quadratic polynomials in this form. Let us start with the first one. Then the first thing that we have to do is just to correct the 2. And we get 2 times x squared plus 2x minus 15. And now we try to write this quadratic polynomial as x plus b times x plus p. How can I do it? X squared plus 2x minus 15. The idea is to consider these two terms as the beginning of the quadratic of a binomial. You see, this is the square of x plus 2 times x times 1. Now I'll complete the expansion of the quadratic of this polynomial, adding 1 and subtracting 1. In such a way, I have again the same beginning, and then minus 15. Now, you see, this is equal to what? Okay, the first part is exactly x plus 1 squared, and then you have minus 16. Now, you have the difference between two squares. And therefore, this is equal exactly to x plus 1 minus 4 times x plus 1 plus 4, which is x minus 3 times x plus 5. Therefore, we get that our initial polynomial, 2x squared plus 4x minus 30, is equal to 2 times x minus 3 times x plus 5. And now consider the other polynomial. The idea is exactly the same. 3x squared plus 7x minus 6 is equal to 3 times x squared plus 7 over 3x minus 2. And now, this polynomial can be written in such a way again. This can be considered as the initial part of the expansion of the square of a binomial. Indeed, this is equal to x squared plus, when you have the expansion of the quadratic of a binomial, you have the square of the first term, then you have 2 times the first term by the second term, and for this reason let me write this in such a way. 2 times 7 over 6 times x plus, now you see, 7 over 6 to the square, and minus 7 over 6 to the square. You see, this gives us no contribution. And then we have minus 2. And you see what I have realized. This part is the square of the binomial. Indeed, you have the square of x plus the square of 7 over 6 plus 2 times 7 over 6 times x. Then this is equal to what? To x plus 7 over 6 square minus this quantity, which is minus 49 over 46 minus 2, which is x plus 7 over 6 square minus, and I have 46 here, 49 here, plus 72, which is equal to x plus plus 7 over 6 square minus, and we have 72 plus 50 would be 122, plus 49 will be 121 over 36. And here again you have the difference between two squares. This is then equal to x plus 7 over 6 plus the root square, the square root of this fraction, which is 11 over 6, times x minus x plus 7 over 6 minus 11 over 6. Therefore, we get that our polynomial 3x squared plus 7 times x minus 6 is equal to 3 times x plus 18 over 6, which is x plus 3, times x plus 7 over 6 minus 11 over 6. 7 over 6 minus 11 over 6 is minus 4 over 6, which is minus 2 over 3. And we get our final result. Ciao.
This is definitely more fun with algebra. Polynomial division, well, there's a classical algorithm called Euclidean division that allows you to divide a polynomial p of x by another polynomial d of x, provided that the degree of d is no greater than that of p. The algorithm will yield an answer of the form p over d is another polynomial q plus another one r over d. Q will be called the quotient, and the point of the remainder r is that it's of degree strictly less than the degree of d. If you multiply across by d, you can write the answer in the form p equals dq plus r. To illustrate the procedure then, we're going to apply this long division, as it's called, to the case of a polynomial of degree 5, which we're dividing by a quadratic polynomial. And here's the setup. You give yourself a scheme like this, where you're going to put the denominator, the divisor, on the right, and the dividend on the left. Now, in some countries, like where I grew up, you put the divisor on the left instead of on the right. This makes really very little difference to the procedure. One can get used to either choice. So the divisor you put here, that's the denominator, d. The dividend, as it's called, is the numerator. You put it on the left. Now, do you see that in writing the numerator, I have included 0 times x to the 4th? That may seem a little odd. It doesn't change anything, but the presence of that term will help us put the powers of x in the right place during the algorithm, as we'll see. We're now ready to begin the first iteration. We take the highest order term of the divisor, that's x squared, and we divide it into the higher order term of the dividend, that's x to the 5th. The result is x cubed. We carefully record the x cubed, and we multiply the x cubed now by every term in the divisor, the 3 terms. That will give us 3 terms on the left. We draw a line, we do a subtraction, and we bring down from the dividend the next term. That was one iteration, and now we're ready to start again. How do we start? With the same x squared, but now divided into the minus x to the 4th. That gives us minus x squared, which we record. We multiply that by all the terms in the divisor. We get the 3 terms on the left. We draw a line, we subtract, we bring down the next term from the dividend. That's another iteration. We continue. The x squared does divide into the minus 2x cubed, and it gives us minus 2x. We multiply that by all the terms in the divisor. We get this, we subtract, and we finally get that, and we bring down the plus 3, and then similarly the next iteration gives us a plus 1. And now, after we perform the subtraction, you will see the term 2x plus 2. Aha! It is now not possible to divide our x squared into 2x plus 2, because 2x plus 2 is only of degree 1. That means we can't go on, which is a sign that we should stop. And we do stop. And this 2x plus 2 is the remainder, capital R. The terms that we have carefully recorded above give us the quotient, q. And the answer to our division then is the quotient plus the remainder over the divisor. To summarize, we've divided p by d, and we've gotten the answer in standard form with the quotient and the remainder over the divisor. Multiplying across by d, we could write p as dq plus r. When the remainder is 0, a 0 function, then we say that p is divisible by d. We'll see that this algorithm for division of polynomials has highly useful consequences for calculating roots of polynomials in the next segment. A theorem means a proposition that is proved by a logical chain of reasoning. We're going to prove a theorem here, the factor theorem, that is extremely useful for finding the roots of polynomials. We're also going to see how the structure of certain proofs works. So here's the statement of the theorem. You're given a polynomial p, and you're given a real number a. And the theorem says that a is a root of p, that is p of a is 0, if and only if the polynomial p of x is divisible by the polynomial x minus a. The restatement of the theorem would be the following. In order for a to be a root of p, it is both necessary and sufficient that p be divisible by x minus a. Now the proof will be in 2 parts, because there are 2 implications to prove. We must prove the left to right and the right to left, as we sometimes say. The first implication to prove is that if a is a root of p, then necessarily p is divisible by x minus a. That's called the necessity part of the proof. The second implication, the converse, is in the reverse order. We want to prove that in order for a to be a root of p, it suffices that p be divisible by x minus a. That's called the sufficiency part of the proof. To do the proof, let's note this initial minus a, we can write, naturally, p in the form q times x minus a plus the remainder. Now, the degree of r, the remainder, is strictly less than the degree of the polynomial x minus a, which has degree 1. Therefore, it follows that the degree of r is 0. That is, r is a constant. So we have this conclusion that p can be written as q times x minus a plus a constant. I'd call that conclusion star, just to have it on hand during the proof. And now the end of the proof. First implication, we wish to show that if a is a root, then p is divisible by x minus a. Well, you look at star, and you see that if a is a root, then putting x equal to a in star immediately tells you that r is 0. When r is 0, that means p is divisible by x minus a, by definition. Second implication,